video is about the substitution rule, and it is a method that we use in integration. And it's helpful when you have kind of a complicated function or a function of a function. It's a just helps straighten things out when you have to integrate something that's a little complicated. So on your sheet you have the rule written down, and it says the substitution rule is if u is a function is equal to g, a function of x, and it's a differentiable function whose range is on some interval, and f is some continuous function, then we can say that if we have this composition f of g of x, and we're integrating f of g of x times the derivative of g of x, the inner function, this is like chain rule, then this is equivalent to the function f of u du, where u is a function of x. And so du is basically g prime of x dx. So the gist of this is we're taking a function and we're defining a function u, and then we're writing it as a new function in terms of u that's easier to integrate. So it's hard to understand right here, but once you get into the method, you kind of can see where things are being placed. So let's just sort of dive into this. Let me just see. Yeah, this is what we're going to do. We're just going to dive into it and get going. Example 1 says we're going to integrate x cubed cosine of x to the fourth plus 2 dx. Okay, there's this is a cosine of a function. So there's a chain rule going on here if you were going to take a derivative. So the idea is to define u to be some function whose derivative, du, you see already sitting up here. So for instance, in this case, I'm going to let u be equal to what this expression is here, x to the fourth plus 2. All right. Then I take the derivative of u, du. Du is equal to 4x cubed. Okay, dx. Now, what I want to do is rewrite the original integral, and I have to account for everything in there in terms of u and du. And can I do that? So what I need is the cosine of x to the fourth plus 2. Well, I can rewrite that as the cosine of u, because that's what x to the fourth plus 2 is. So that takes care of that part. I can do that part. Also, I need an x cubed dx. Well, when I have du, it's equal to 4x cubed dx. So this 4 is in the way, but I can handle that pretty easily by just dividing both sides by 4. And so when I do that, if I say 1/4 du, that's equal to x cubed dx, and that took care of everything I need. So let's rewrite this. This is going to be the integral. That integral symbol's free. If I ever have a constant, my habit is to write it over on the outside. You can write it inside, it's fine. But by writing down 1/4 du, what did I accomplish? Well, that accomplished x cubed dx. So I've got that part and that part. What I have left is to write down the cosine of x to the fourth plus 2, and I can do that by writing down the cosine of u. So now we can just integrate this function, and when we do, we say, okay, whose derivative is cosine of u? And that would be sine. So the integral of cosine u is sine. So 1/4 the sine of u plus some constant. Okay, now we rewrite everything in terms of the original variable, which was x. So our final answer is going to be 1/4 the sine of x to the fourth plus 2 plus some constant. So this is our answer for this one. All right, let's try this guy over here. The integral of x over the square root of 1 minus 4x squared dx. So we're going to try the substitution, by substitution. Say, well, what can we let u be that would be helpful to us? So here's something complicated. And so when you're doing this method, it's not automatic. You're like, oh, automatically I always let u be this. Sometimes you have to try stuff to see if it's going to work. but you're trying to let u be something whose derivative you see in the integral. So u, in this case, I'm going to let u equal to, I'm going to try 1 minus 4x squared. If I could let it be the square root of 1 minus 4x squared, but then when I take the derivative, I'm going to have all this power rule 1/2 times this to the negative 1/2, and that's going to be hard to clean up. So that's why I decided just to let u be this, because when I take the derivative of the 1, it goes away, it's a 0, it's a constant. And then I'm left with something times x. Now, the fact that it's got a constant in front of the x is not an issue, just because like over here, we had the 4x cubed and we wanted to get rid of the 4. We can divide that off, so that's not really a big deal. So I'm going to let it be this because the derivative of this will have an x in it, and I see that I need an x in it. So let's continue. Du is equal to 0 minus 8x dx. And so this is what du is equal to. All right. If I want to rewrite this original integral in terms of u, this will become the integral. You just get to write the integral sign down. I need an x dx, and I have a negative 8x dx. So if I divide both sides by negative 8, I can accomplish that. Divide this side by negative 8 and this side by negative 8. So negative 1/8 du gives me the x dx. So I'm going to write that down. All right. This is just my habit. You can write the negative 1/8 in there. It's fine. So by writing that down, what did I get? I got x dx, that part and that part. What I have left to accomplish is to write down 1 divided by the square root of 1 minus 4x squared. So 1 divided by the square root of u, because that's what I said u was. So now we just have to integrate this. All right, so I like to write my square roots as power. So if I rewrite square root of x, I can rewrite that as, the square root of u to the 1/2. And then if I cross the fraction bar, it becomes a negative 1/2. So this is equivalent to negative 1/8, the integral of u to the negative 1/2 du, like that. Now we just integrate this, power rule. So this is negative 1/8. U to the negative 1/2 plus 1 is 1/2 divided by 1/2 plus a constant. Negative 1/8 divided by 1/2 is a sort of a keep, change, flip. So this becomes negative 1/8 times 2 over 1. These fractions here. So this becomes a negative 1/4 times u to the 1/2, or the square root of u. Or changing it back into its original variable, the square root of 1 minus 4x squared plus a constant, because it was an indefinite integral. All right, before I move on, I'm just going to check and make sure I didn't make a mistake. Do I like that answer? Negative 1/4, da 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 da. Yes. Do I like this answer? 1/4. Yep, that's okay. So here's a couple more examples. Let's integrate this one. I'll show you sometimes some other things that can happen where you can still use the substitution rule, but you might have to do an extra step. So let's have a look at this guy. Alrighty. Let's do example 3 is the integral of the square root of 1 plus x squared times x to the 5th dx. Okay, this is number 3. All right, so this one is a little bit, you got to do something extra in here. So it's a little bit hard. If you let u be 1 plus x squared, du would be 2x. So we have an x, and we really need an x to the 5th. But we can work with that, and I'll show you how we can work with that. We're going to go ahead with that, guys. This is what we'll do. We will let u be 1 plus x squared. Then du is equal to 2x. And so I need a x to the 5th dx, not a 2x dx. Let me take care of this 2 by dividing it. Oops. Dividing both sides by 2. So 1/2 du is x dx. Alright, so by writing down this, what did I accomplish? 1/2 the integral of du. What does that give me? That gives me 1x dx. What do I have left to accomplish? I have left to accomplish an x to the 4th and the square root of 1 plus x squared. Okay, how can I get the square root of 1 plus x squared? Well, I can say that's u to the 1/2. So by u to the 1/2, by writing that down, that took care of this. So I've got this much, I've got this much. I have to figure out how to get x to the 4th. Well, if you look up here, at u is equal to 1 plus x squared. I can solve this for x squared. U minus 1 is equal to x squared. And then, if I square this, I get x to the 4th. U squared minus 2u plus 1. And that's how I can get my x to the 4th in terms of u. So I went back up to this equation, I solved it for x squared, and I squared it to get my x to the 4th. So let's see, what does that get me? All right, I'll move you over. U squared minus 2u plus 1. This gives me this. Something that I can easily integrate. I will distribute the u to the 1/2, combine exponent powers, and integrate each one using power rule. That makes it super easy. 1/2. The integral of u to the 1/2 plus 2 is 5/2 minus 2 u to the 1 plus 1/2 is 3/2 plus u to the 1/2 du. Now we just power rule, integrate. So it's 1/2 times u to the 5/2 plus 1 is 7/2 divided by 7/2. Minus 2 u to the 3/2 plus 1 is 5/2 divided by 5/2 plus u to the 1/2 plus 1 is 3/2 divided by 3/2 plus a constant. Alright, so all of this can be written as 1/2 times 2 over 7 u to the 7 over 2 minus 1/2 times 2 is a 1. I just get 2/5 u to the 5/2 plus 1/2 times 2/3 u to the 3/2 plus a constant. Rewriting everybody in terms of the original variable x, I get 1/7 1 plus x squared to the 7 over 2 minus 2/5 1 plus x squared to the 5/2. These 2's will cancel. Plus 1/3 1 plus x squared to the 3/2 plus a constant. And that's your answer for number 3. Alrighty. Let me see if I like my answer. And I do. Okay, let's do number 4. Number 4 is the integral of the tangent of x dx. Okay, so let's what I like to do here is maybe break this down into sine and cosine. So let's see what happens when we do that. So tangent is really the integral of the sine of x over the cosine of x dx. Okay. What could we do with this? Well, let's try u substitution. Let's let u equal to something whose derivative we see sitting there. So the choices kind of are let u be sine x or let u be cosine x. So you could try both of those and see which one worked. Here's what I see sitting there in the numerator is the sine x dx. That whose derivative is a form of sine, cosine's derivative is. So that's going to lead me, after you do some trial and error, you'll see this as well, to let u equal to cosine of x. So let's let u equal to the cosine of x. Okay, then what is du? then du is equal to negative sine of x dx. Now the negative, as you've seen, is not a problem. Constants, we can divide it off. So divide both sides. Negative du is the sine of x dx. How's this going to help me? Well, I need sine x dx, and I have that just by writing down negative du. I have accomplished that. So negative du gives me the sine x dx. Okay. Then I just have to write 1 over the cosine of x, or 1 over u, just like that. So this, let's integrate this. When we integrate this, du over u, or 1 over u, is the natural log. This is the negative, the natural log of the absolute value of u, plus a constant, or negative, the natural log of the absolute value of cosine of x, plus a constant. Now this is true. However, the integral of tangent is known to be the natural log of the secant of x. So let me show you how they get that. This is log property, the log law power rule. When you have a log of something, when you have the log of base a of m to a power, you can take the power and write it in the front. This is a power rule. So what they're going to do, and you can also take the power and kick it back up, that's in the front, and kick it back up when you have a log expression. So this is what they do. They take this negative 1 right here, and they take this power, and they're going to kick it up up here using this log property, coming from this way to this way. All right, you're allowed to do that, and so when we do that, this is equivalent to the natural log of the absolute value of cosine of x to the negative 1 plus some constant. But cosine of x to the negative 1 is 1 over the cosine of x, and that's known as the secant of x. So many times you will see that the integral of tangent, which we're going to need later, is equivalent to the natural log of the secant of x plus a constant. So I wanted to kind of develop that one with you. All right, 2 more examples, and then we're done with this one. These are definite integrals. They have limits. So let's go ahead and do the last 2. And I'm hoping that the substitution rule is something that you are familiar with and that you learned in Calc 1. So if you didn't, you're learning it now. But hopefully this is start to this is not too rocky, that you've seen this stuff before. But let's do these last 2. Example 5 says, let's find the integral of from 0 to 3, the limits of integration are 0 to 3 of dx over 5x plus 1. All right, and then the number 6 is the integral from 0 to pi over 2 cosine of x times the sine of the sine of x dx. All right, let's do these. So it goes like this. Right here, if we're going to use, oops, no, I got my dx. If we're going to use the substitution rule, we want to let u equal to something that's going to kind of make it less complicated and whose derivative we see there. If I let u equal 5x plus 1, that would take care of kind of a lot. The derivative of 5x plus 1 is going to be 5 dx. The 5 is not a problem, and I just need a dx, so I'm going to go with that. So let's let u equal to 5x plus 1. Then du is equal to 5 dx. And if I just want a dx, I can say 1/5 du is dx. Okay, then I can rewrite this in terms of u pretty easily. So what do I do with the limits? You have 2 options. I'm going to show you both options, and either way you choose to do it is fine. First, let's rewrite it. 1/5 du. By writing down 1/5 du, I got the dx. Now I have to write 1 over u. 1 over 5x plus 1, 1 over u will give me that. Now what do I do with the limits? Here's my 2 options. One option is to just remember, put little placeholders here. Remember, you have limits on this guy. And keep reminding yourself you've got limits on it until you turn it back into the original variable x and then put in the original limits. That's one option. So I'll do that first. 1/5, let's integrate this. When I integrate this, du over u is the natural log of u, and so it's going to be evaluated at these limits. Okay, this is my placeholders. Now I substitute in what u was really. This is the natural log of 5x plus 1, the absolute value of 5x plus 1. And now I put in my original limit, 0 to 3. All right, so this is 1/5, the natural log of 5 times 3 is 15 plus 1, 16. Minus 1/5, the natural log of 5 times 0 is 0, plus 1 is 1. Well, the natural log of 1 is 0, so I end up getting 1/5, the natural log of 16. All right, that's that. Here's a second way you can do it. The second way you can do it is to adjust the limits in terms of u. And so we're going to integrate du over u, but right here, we'll go ahead and change these limits. How do you do that? Well, if x is 0, you plug in this lower limit, 0 for x, right here where you said, what is u? So if I let x be 0, 5 times 0 is 0, plus 1, u would be 1. My lower limit turns into a 1. If x is 3, I go here and I plug in the 3. 5 times 3 is 15, plus 1 is 16. My upper limit is 16. And you can change the limits in terms of u. If you do that for a definite integral, you do not have to go back and put it in terms of the original variable. So we get 1/5, the natural log of u evaluated 1 to 16. All right, so this is 1/5, the natural log of 16, minus 1/5, the natural log of 1. The natural log of 1 is 0, so our answer is 1/5, the natural log of 16. All right, that's kind of up to you how you want to deal with your limits right there. Let's handle this guy. What should we let u be? I'm going to let u be sine of x because the derivative of sine of x is cosine x, and I see its derivative sitting there. So that's how I'm going to choose my u. So I'm going to let u equal to the sine of x. Then my du is going to be the cosine of x, dx. So by writing down du, that's all I wrote down, I took care of the cosine and the dx. What I have left to write down is the sine of sine x, so that would just be the sine of u took care of that. All right, so in this case, I'm just going to go ahead and change my limits in terms of u and not look back into x. So let's do that. Right here, 0. I let x be 0. So what is the sine of 0? I draw a unit circle, and this is my angle 0, and this is the point 1, 0, and the sine is the y value. So the sine of angle 0 is 0. So that's still going to be a 0 right there. All right, now if I put in pi over 2, the sine of pi over 2. This is pi over 2 right here, 0, 1. The sine is the y value, so it's going to turn into, the sine of pi over 2 is 1. So I changed my u limits right there. All right, let's integrate. Whose derivative, who can I take the derivative of and get sine, u, negative cosine of x, right? Negative cosine of u, I would say. If you're ever unsure if you did a good job integrating, just take the derivative of your answer at the end and see if you get back to the integrand. So let's try that. What is the derivative of negative cosine of x? It would be negative sine of x, and that would give me that. So that's good. All right, so let's do it from 0 to 1. So this is negative the cosine of 1 minus negative cosine of 0. Okay. I get negative the cosine of 1, which is radians, 1 radians, plus the cosine of 0. Cosine of 0, oh, here's angle 0. The cosine is the x value. That's a 1. I don't know what the cosine of 1 is. I could plug it in my calculator. I don't want to. I'm going to leave it in exact form. So this is 1 minus the cosine of 1. And that's the answer to that one. Okay, at the very bottom of the sheet, that you have. I have listed a couple of symmetry, just a couple of rules. So real quick, if f is even, an even function is one that's symmetric across the y-axis. And so if you're integrating an even function from negative a to a, or negative 4 to 4, or negative 2 to positive 2, something like that, that's equivalent to 2 times the integral of it from 0 to a. So an even function, let me just show you a picture of an even function. Y equals to x squared is a good one to look at. It's symmetric across the y. So that means if I was integrating, let's say from negative a to a, and you know integration is area under the curve, this is symmetric, so these are equivalent areas. So it's really 2 times this area. That's why you have that rule right there. The second rule, if f is odd, then you can integrate from negative a to a and it's equal to 0. Why is that? Here is a picture of an odd function, which is symmetric about the origin, x cubed, and it looks like this. Let's see. Oh, I missed. Let me try again. Looks like this. Okay, so let's say we're going to integrate from negative a to a. Well, these areas are equivalent, only this is going to be negative because it's underneath the x-axis, and this is going to be positive. And so these will cancel each other out. So if we integrate here, add this area to this area, remember when you integrate its net area, that's why it's 0 if it's an odd function. That's what those 2 rules at the bottom mean. Alrighty.